Hello! One of the things that's really useful when working in automata theory is the ability to think about a generic finite monoid. So how can we do that? What do finite monoids look like? I actually want to start with a question that maybe you've seen before if you've done any group theory, and that is, what does a finite group look like? How can we reason about a generic finite group? So given a particular element A of a group G, we have a function f sub A, which takes in elements of our group and outputs elements of our group, that simply takes in an element and multiplies it on the left by A. In a generic group, the order that you multiply things in matters, just like it does in a monoid. There are some groups and some monoids where the order that you multiply things in doesn't matter, and we call those commutative or abelian groups and monoids. But in general, the order matters, and so I'll make sure that the order that things show up on this side is the same as the order that things show up on this side. This function here, you can show, is actually a permutation of the elements of G. And f sub e, where e is the identity element of the group, is the identity function. This process here is essentially looking at a group as acting on itself. That is, the element A acts on various elements of the group just by multiplying by that element. And this is a very nice perspective on our functions, not only because the identity element of the group corresponds to the identity function, but also because multiplication in our group corresponds to composition of functions. If we have two elements of our group, A and B, well, of course, A times B is going to be an element of our group, and so we'll have a function corresponding to that element of our group, and what that function does to a particular value of x is the same thing as what would happen if we took our x and applied f sub b to it, and then applied f sub a to the result. And so f sub ab is f sub a of f sub b. So what we have here is actually an isomorphism between our group and some collection of functions acting on the group. There's an isomorphism between our group with its notion of multiplication and its identity element, and the set of all functions that we wind up getting in this way under composition with the identity function corresponding to the identity element of the group. And if we're talking about a collection of functions on some finite set, their structure, their interrelationships, don't actually depend on the names of the elements of that finite set. We could think of these functions as just acting on numbers from 0 to n. Let's take a look at a concrete example. Let's take the group Z3. This has 3 elements and has a multiplication table that looks like this. If we want to multiply B by A, we get E. So B and A are inverses of each other. E is, of course, the identity element. If you multiply anything by E, you get that thing. And if you multiply E by anything, you get that thing. Now let's take a look at the various functions that each of these elements wind up corresponding to. Of course, f sub e acts as the identity function. F sub a behaves like this. And f sub b behaves like this. And again, the key thing was that when we composed, for instance, if we compose f sub a and f sub a, that should give us f sub a times a, which is b. So if I compose this function with itself, I should get this function here. That the functions under composition behave identically to the group elements. And again, the behavior of these functions in relationship to each other doesn't depend on what the names of the elements that we're plugging into these functions are. So let's change the names of the inputs and outputs to 0, 1, and 2. Again, we haven't changed the interrelationship of these functions. F sub a of f sub a is still going to be f sub b. F sub a of f sub b is still going to be f sub a times b, which is equal to e. So f sub a and f sub b are inverse functions to each other. So this is how we can view our original group as a collection of permutations. We haven't included all of the permutations on 3 elements. There are a total of 6, and we've ignored half of them. But you can do this for any finite group, to view that finite group as some collection of permutations on a finite set. And actually, you can do this with infinite groups too. It's just permutations on some infinite set. It's also worth noting that depending on how you associate numbers to these individual elements, you might wind up getting different permutations as a result. Of course, f sub e is always going to be the identity map, but we could swap f sub a and f sub b if we picked our numbering differently. We can also turn our functions into matrices. Each of these is a permutation, and so we can think about applying that permutation to the elements of a vector. This operation is a linear operation on a finite dimensional vector space, so it corresponds to a matrix. Of course, since the permutation f sub e doesn't do anything, m sub e doesn't move the corresponding components of any of these vectors. And so it's just going to take these basis vectors to themselves. And if you remember, the rule for determining the matrix that you get is you take your operation, multiply it by the first basis vector, multiply it by the second basis vector, multiply it by the third basis vector. This gives you 3 vectors, and you just put them next to each other. From this, from this, from this. And so this is our matrix corresponding to this function here, and thus also corresponding to the identity element in our group. What happens when we apply this permutation to the components of our basis vector? Well, it takes this 1 in the 0th component of the vector and moves it to the first component of the vector. It takes this 1 in the first component of the vector and moves it to the second component of the vector. And it takes this 1 in the second component of the vector and moves it to the 0th component of the vector. And so again, if we take these 3 vectors and stack them next to each other, we're going to wind up with a matrix representing this function here. And the same for m sub b. And again, this collection of matrices under matrix multiplication is isomorphic to our original group and our collection of permutation functions. So for instance, m sub a times m sub b is going to be equal to m sub e. We could either multiply these out as matrices, or we can multiply the corresponding elements of the group, and a times b is equal to e. Similarly, if we wanted to invert a matrix like m sub a, we would simply have to figure out what is the inverse of a. The inverse of a is b, and so this is going to be m sub b. These 2 matrices are inverses of each other. We can do the exact same thing that we did with finite groups with finite monoids. We simply have to drop the requirement, right? So a group is a monoid that all elements have inverses in. And so we'll have to drop the requirement that all of the functions in our collection, or all of the matrices in our collection, are also going to have inverses in our collection. And in fact, we're going to have to drop the requirement that those functions and matrices be invertible at all. But otherwise, the process is exactly the same. Let's take a look at an example monoid. This here is the multiplication table for some 5-element monoid. This monoid happens to be non-commutative. For instance, d times a is equal to d, whereas a times d is equal to a. The order that you multiply things in matters, and so I want to be really clear on the convention that I'm using for these multiplication tables. If we're multiplying together two elements of our monoid, I'm going to want this to be the first multiplicand and this to be the second multiplicand. So again, in order to figure out d times a, we need to find the d from here and the a from here, and that tells us that d times a is d, and a times d, we need to look up the a here and the d here, and that tells us that it's a. I'm not sure if there's a standard convention for multiplication tables for non-commutative sorts of multiplication, but this is the standard that I like to use. It's worth noting that not every multiplication table gives us a monoid. We need to check first closure. Closure just says that every element on this table is one of the elements of our structure. So we have to make sure that there aren't any other letters or other things that aren't elements of our structure somewhere on the table. That's easy, and it's also easy to check that E acts as an identity element, just by looking at the top row and the first column. Checking associativity, on the other hand, is really tricky. As far as I can tell, there's no really good way of just looking at a multiplication table and determining if it's associative. I had to actually test this on a computer, and in fact I had a computer search looking for associative multiplication tables in order to get this monoid. Just as before, for each element of our monoid, we can consider the function which multiplies by that element of the monoid on the left. So for instance, f sub a of x is going to be a times x, as opposed to x times a, which might be different. As we would expect, f sub e is just the identity function. F sub a winds up being a constant function, just outputting a. F sub b winds up being some permutation. F sub c winds up being another constant function. And f sub d winds up being somewhere in between a permutation and a constant function. Just as before, true multiplication facts in our monoid translate into true composition facts for our functions. For instance, b times c is equal to c, and so we expect that f sub b of f sub c is going to be equal to f sub c. Again, we have a monoid homomorphism. We're looking at the same structure, it's just that we're calling the elements different things. We've effectively changed the names of these elements from b to f sub b, for instance, but the structure, the interrelationship of these things, remains exactly the same. And thus, so does the first order properties. Just as before, we can view these functions as not acting on the monoid, but as acting on an arbitrary 5-element set. For instance, the numbers 0 to 4. Changing the names of the inputs and outputs to these functions doesn't affect their interrelationships in terms of what compositions are equal to what compositions. Unlike in the group case, these functions aren't necessarily permutations. Again, some of them are constant functions, and f sub d is somewhere in between. But otherwise, we have exactly the same fact that we had in the group case. Every finite monoid can be viewed as essentially a submonoid of the collections of functions on some finite set under composition. Just as before, we can also turn these functions into matrices. Again, we want it to be the case that we're taking the function f and we're turning it into a matrix M, where M multiplied by the ith basis element is equal to the f of ith basis element. So again, we can do that, and we get matrices. These aren't permutation matrices necessarily, but these matrices are all zeros and ones, and they have exactly 1, 1 in each column. And again, we have some sort of isomorphism. This collection of matrices under multiplication forms a monoid, and that monoid is isomorphic to our original monoid under its notion of multiplication, just via the obvious translation of translating an element to m sub that element. So we have this result that if you want to think about some finite monoid, you don't lose any generality by thinking about a collection of matrices under matrix multiplication. Every monoid can be represented in this way. So the choice is yours. If you want, you can think about abstract monoids with some sort of multiplication table. If you want, you can think about finite monoids as just collections of functions under composition. Or you can think about finite monoids as collections of matrices under matrix multiplication. One of the nice things about working with matrices, though, is that it's very easy to reverse the notion of multiplication. Very often when we're talking about non-commutative groups or monoids, we'll be interested in thinking about what would happen if we took the monoid that had exactly the same multiplication but in reverse. So here I've just taken the multiplication table and flipped it over. This gives us a structurally different monoid. If we thought maybe these two monoids are isomorphic, but somehow the names of the elements are scrambled with respect to each other, well, that can't actually be the case. We have one element where multiplying by it on the left gives us just that element. But we don't have such an element over here. We have a logical property that's true of this structure that's not true of this structure. And so they can't be isomorphic. One of the nice things about presenting these monoids as matrices is that all we need to do is take the matrices for this monoid and take their transposes, and that gives us the matrices for this monoid here. It's not going to be the same matrices that we get if we do the construction directly, but it is going to give us another set of matrices that can be used to represent this monoid here. There's actually lots of different collections of matrices that represent any one particular monoid. And there's a really interesting branch of abstract algebra called representation theory that focuses on mostly groups, taking a group and figuring out how to represent it in terms of matrices. In this video, all of our matrices entries were either zeros or ones, but allowing them to be potentially other numbers might unlock some additional options that, for instance, maybe allow you to reduce the dimensionality of the matrices. The property of matrices that allows us to go from this structure to this structure is simply that matrix transposition reverses the order of multiplication. And so by transposing all of our matrices for the first monoid, we can create matrices for the second monoid. So thanks for watching. I hope you got out of this a better intuition for how to think about arbitrary finite monoids. Let me know if you have any questions or comments down below, and I hope to see you in a future video.